a vector field is a function that assigns to any point in the space, so for instance to each point, a vector. So in that way we are going to have that for each point in the space we will have associated a vector. Depending on the function, the vector can be anywhere, right? So each function will have some particular vectors, but in general we will have for any point in the space a vector associated. So the evaluation of the vector field, for instance, at this point, well, will be, for instance, this vector. At this point, well, for instance, this vector. At this point, for instance, this vector. So at each point of the space, we'll associate a vector. And this space can be R2, R3, any Rn. So for example, let's see this vector field. So this is a vector field that associates to each point xy in the two-dimensional space, associate the vector minus yx. Another possible notation will be this way. We can say that to each point xy, associate the vector minus yi plus xj, right? Which is the same thing that saying the vector minus yx. That is this more abbreviated notation. So this will be then one example of a vector field. So what will be the drawing of this vector field? Well, we will have to give points here, random x, y points, and calculate images of the point. So if this is the x, y axis, so we're going to just plot some points to see what particular vectors this vector field assigns to each point in R2. So for instance, let's give some values like 1, 0, let's say. So the point 1, 0 will be 1 of x, 0 of y. So this will be the point 1, 0. So let's see what vector is associated. Well, plugging in here 1, 0, we have that this is minus 0, which will be 0, and here is x, which is 1. So it associates the vector 0, 1. So the vector 0, 1 is 0 for x, 1 for y. So will be a vector of norm 1 that points that direction. So this is the vector 0, 1. Let's see what vector is associated, let's say, to this other point, 2, 0. So we do the same. So we put 2 here, 0 here. So the vector associated will be minus 0, that will be 0 again, and x is 2, 0, 2. So we have that at this point, the vector is 0, again, of x, 2 of y. So will be something like this, a longer vector. And then we can keep putting here any point. We have all the points in the space here, right? To give values, we can choose whatever we like. So for instance, let me plug in the point 1/2, 1. So 1/2, 1 will be like here is 1/2, here is 1, so this point. So let's find out what is the vector associated to that point. Again, we plug it in here 1/2, 1, and the result is going to be then minus 1, comma x, which is 1/2. So the vector here is going to be the vector minus 1 of x, 1/2 of y. So I go 1 unit here and half unit here. So the vector that we have associated here will be something like this. And so let's give just more values. Let's say f at 0, 1. So 0, 1 will be this point here, 0 of x, 1 of y. So let's plug in again here, and the image of 0, 1 is minus 1, 0. So at this point then we have minus 1 of x and 0 of y. So will be a vector that goes like this. And let's continue some other one, f at, let's say, minus 1, 0. minus 1, 0 will be this point here. So we evaluate here, and the result here is 0 minus 1. So 0 of x minus 1 of y, something like this. Well, you see that this is kind of labor intensive, right? To try to plug in for all the points here. Here is where we should have some help with the computer that could plot more points faster. But essentially the idea, what the computer will do, is exactly what we are doing here, getting some points and finding out what the vector is. So let's see how Sage will plot our vector field. Remember, the vector field is minus yx, and I'm giving this window here for the values of x, y. We can use actually essentially any window here. And so here we see what is the plotting that the computer does with more points here. So in particular, we have the ones that we have calculated ourselves, but we see that if we put here with points that are closer to the origin, you see that in this case the norm of the vector becomes very small, right? We see here that the vectors are smaller. Here we see that the norm of the vectors are a little bigger, but also observe the directions that the vectors are, which is consistent with the first ones that we calculate by hand. Let's check some other examples. So this one will be in 3 dimensions. I mean, the vector field can be in any number, we said, in any space Rn. So in this case, we are consider this vector field, the one that is components are minus y 3z for x, for the second component is x, and the third component is x plus z. And I'm giving this window to draw it. And let's see how Sage draw this vector field. We can see here the vectors with different colors to distinguish them, but you can see, according where you are, you can see the norm of the vectors, how they are becoming bigger in some places, and what is also the slope, how this thing is changing, and you can see it from different point of view. Another example, you can see this one, minus yz e to the minus xy, etc. And this will be the plotting of the vectors by Sage. One example, very important example of vector field, is one that should be familiar to you, that we have already mentioned before. So this function that we have here, the gradient of a real function. I mean, this is a function f that is a function of 3 variables. I mean, small case f is a function of 3 variables with values in R. We have seen those functions before, that we can calculate the partial derivatives, the directional derivatives, etc. Well, if we calculate the gradient of this function, meaning the derivative respect to x, respect to y, and respect to z, so that is an example of vector field, because it's a function, capital F now, that to each point in the space x, y, z associate a vector, and this vector is given by the partial derivative respect to x, respect to y, and respect to z. For example, let's find the gradient vector, and this vector field, by the way, is called gradient vector field. So let's find the gradient vector field associated to this function. So this is a function of 3 variables with values in R, and we can calculate what will be the gradient vector field associated to it. Essentially, all what we have to calculate is the gradient, I mean the partial derivative with respect to x, y, and z. So if this is the function, let's calculate then the derivative respect to x of this function. Observe that here z will be a constant that goes out of the derivative, so that will be z times the derivative of e to the minus x. That will be e to the minus xy. That will be x to the minus xy times, by chain rule, the derivative of this. We are doing the derivative respect to x. The derivative is minus y, so I'm putting here minus y in front. And so the second derivative, I mean the derivative of this respect to y, will be the same thing. Here, this is a constant. The z goes out of the integral, and we need to do the derivative now of this part. E to something, the derivative is itself times, by chain rule, the derivative of this now respect to y. The derivative will be minus x. And finally, the derivative of this respect to z. Now, the derivative respect to z is a constant times z. So the derivative is just this constant. So this will be the gradient, right? So this will be just the derivative respect to x, the derivative respect to y, and the derivative respect to z. So the whole vector here is the gradient. So this function given like this, I mean that to each x, y, z associate this vector, so this is a vector field, and this is because we obtain it in this way by calculating the gradient of this function, is what is called the gradient vector field. And the function that this one comes from is what is called the potential of the gradient vector field. Let's come back to the plotting of this vector field in Sage. So we have this is the function that we just calculate, right? This one that is the gradient of the function given. So we can see here how this vector field looks like at each point here. Moreover, in our case, we know where this vector field comes from, right? Because we calculate this as the partial derivatives of a function. We're going to say that a vector field is called conservative when is actually the gradient of something. I mean, when exists a function such that the gradient of that function is the vector field. So, for instance, this vector field here is conservative since by the way that we calculate, we know that is the gradient of this. So, this vector field, the ones that come from some function, are going to be called conservative vector fields. And the function that they come from are going to be called the potential of that function. So, for instance, let's suppose that we have a function f of xy equals x squared plus 3y squared. If we calculate the gradient vector field of this one, so the gradient of f is equal to the derivative respect to x is 2x, the derivative respect to y is 6y. So this vector field, let's call capital F, this vector field is conservative because we just calculated as the gradient of this one. So this vector field is conservative and the potential function is this one, the small case f. Let's see how this function actually graphs. So this is the vector field that we just calculate, right? 2x, 6y, and I'm giving here some window to draw. So the arrows that we see here is the actual drawing of our vector field. But also I'm introducing in this graph something else that we knew about the original function, the potential function. This function is x squared plus 3y squared. Well, we know how to calculate the counterplot, which is just the level curves here. So this curve, these ellipses that we see here, these ones here, so these ellipses are actually the level curves of this potential. And so see what happened when I draw both together. So we see that the vector field, which was calculated as the gradient of this function, is actually perpendicular to the level curves at all points here. So that's what's going to happen in general. So we have a potential function and we calculate the level curves of the potential function. This is the potential function, and we calculate here the level curves. So perpendicular to these level curves is going to be the gradient vector field. So these vector fields that we see that we saw that they were conservative because we actually calculate them as gradients. Sometimes we have given the actual vector field just directly. So how do we know if this vector field actually comes from a potential function or not? I mean, how do we know if there exists some function f such that the gradient of f is actually f? So we don't know, just given the vector field, if it is coming from a potential function or not. I mean, if it's the gradient of some function or not. Well, what we can observe, because we know some properties of the partial derivatives, is that if our vector field has two components, let's call it like here m and n, first and second component. So suppose that the first component were actually the partial derivative of f respect to x, and suppose that the second component were really the partial derivative respect to y. So let's suppose that this function f really exists. So if that happens, so when we actually do the derivative of m with respect to y, I mean with respect to the other variable, let's say if we do the derivative of m respect to y, so what we are doing is the derivative respect to y of the derivative respect to x, right? The derivative of f respect to x. And we know that this is nothing but the second derivative of f respect to y and x. And if we do with this one, with the component n, we do the derivative respect to x. So what we are doing is just the derivative respect to x of what? Of the derivative respect to y. And this is nothing but the second derivative of f respect to x and y. And we know, we have seen before, that these two mixed derivatives actually should coincide. They have to be equal. And so, what are we saying at the end of the day? Well, that this derivative and this derivative have to be equal. And so we have a criterion, a characterization of vector fields that says then that if the actual vector field is conservative, then this derivative has to be equal. So that will give a way to actually say if a vector field is conservative or not. We just calculate these partial derivatives. I mean, we take the first component and we do the derivative respect to y. And we take the second one and we do the derivative respect to x. So if these ones do not coincide, so then this one cannot be conservative. Observe that this criterion allows us to decide if a vector field is not conservative, but is not a criterion to decide that it is, since this is an if-then condition. So if the two derivatives do not coincide, then we can say that it's not conservative, but not the other way around. Later on, we will see that with some hypotheses added, also will be in the other direction. But so far, this result is only to prove that the vector field is not conservative. And we have an analogous characterization for when the function has three components. So we have more cross derivatives here, more mixed derivatives, and so it's all these, then all these things are the ones that have to coincide. So for instance, let's check if this vector field given like this is conservative. I mean, the question is does really exist a function f such that this is the gradient of something? Well, that will be very hard to find by hand if this function exists such that the derivative is that. But we have this condition of the mixed derivatives to try. In a simple connected domain, these are going to be equivalent, so we can just rely in the mixed derivative result. So let's start by calculating the derivative of m, I mean of the first component, with respect to y, right? So these are the derivatives that we have to compare. the derivative of m respect to y. Okay, so let's focus in this one. This is a quotient, so the derivative is going to be a quotient, and the formula is the derivative of the first one, and remember the derivative is respect to y in this case. So the derivative of the first one respect to y is going to be 2x times the second one just as it is, minus the first one as it is, times the derivative of the second one, again, respect to y. So observe that the derivative of this respect to y, this part is constant, so it's just the derivative of this respect to y. So it's just to y. And the quotient should be the denominator squared. Observe that in the numerator we have in common 2x and 2x. I'm going to take it as a common factor, 2x, and remains everything else, right, in both sides. So in this case would be this that I'm also going to expand it. So the square of this is going to be 1 minus 2x squared plus x to the fourth power plus y squared. So that's this. And now minus this, that is minus 2y squared. And everything divided by this denominator. So let's keep simplifying what we have inside here. And this is going to be equals to 2x times, let's put together since here, we're going to have here 1 minus 2x squared plus x to the 4, and here y squared minus 2y squared, this is just minus y squared, and divided by the whole denominator. Okay, so this is the derivative of m respect to y. So let's continue now with the derivative of m respect to x. Again, it's going to be a quotient because this other part, the n, is also a quotient. Now we have to center in looking at this one. So we start the derivative of this quotient, and now with respect to x. So will be the derivative of the numerator, which is minus 2x times the denominator as it is, minus the first one as it is, times the derivative of the denominator, and now the derivative is with respect to x, so this part is going to be constant, and we are going to center in the derivative of this term, which is it's a power, right? So it will be 2 comes down times 1 minus x squared to the power 1 times, by chain rule, the derivative of whatever is inside, which is minus 2x, and divided by the denominator squared. The denominator is the same one. So let's continue the operations in these two terms. Observe that we have in common minus 2x in both. So I'm going to take minus 2x as a common factor, times, and so in the first one remains this one that we have already expanded before. So this is going to be 1 minus 2x squared plus x to the 4 plus y squared. And in the second one is going to be all this. So this is going to be minus, let's do this operation this way. We have a 2 here and here. Observe that we have 1 minus x squared times 1 minus x squared. So that's a square, right? So it's 1 minus x squared squared, so that will be 1 minus 2x squared plus x to the 4, and divided this square. Let's continue this operation here. So we're going to have here the minus 2x outside, and let's continue. Let's eliminate this parenthesis now. And now I'm going to multiply the 2 by all that. So that will be minus 2 plus 4x squared minus, right, plus minus 2x to the 4. And divided this in square. So let's start putting together common terms. In numbers we have 1 minus 2, that is minus 1. For x squared we have this and this. 4x squared minus 2x squared is plus 2x squared. For x to the 4 we have this one and this one. That will be minus x to the 4. And the remaining is just y squared here, and that's it. Okay, so let's do the last multiplication by minus 2. We are going to have here, let's just get this minus multiplying the whole thing. That will be 2x times, we change the sign of this, right? So that will be 1 minus 2x squared plus x to the 4 minus y squared dividing this square. Okay, so this one then is the derivative of n respect to x. So now let's compare this one. So is this actually the same like this? Well, we can see that it's exactly the same, right? So we got one in a very different way, but we got exactly everything the same. So we can say that this vector field is conservative in any simple connected domain. We cannot say just because it satisfies this condition, since this is an if-then condition. So we know that this condition is true, but that doesn't tell us that the vector field is conservative. But we will see later that if the domain is simple connected, so then it's going to be conservative. So we can say that in this example, this vector field is conservative in any simple connected domain.